welcome back. So today what we're going to be talking about is work, which you might think, well, we're always doing work, but this is the particular technical usage of the word work that happens in physics. So in physics, the notion of work is really, really important. It is connected to energy in physics, and well, all of energy and stuff. This is really important because of a result known as Noether's theorem by Emmy Noether, the really famous mathematician. And her result is kind of why all of this stuff, well, it gives a deep mathematical understanding of why all this stuff matters. But suffice it to say that work is a very important concept in physics, and what we're going to see with this is that it provides us with yet another application of integration and how that kind of thing plays a role in the real world. So not all of you are going to necessarily be doing a lot with physics, but it is a good illustration of how to see where integration comes up in certain contexts. So work, if we have a constant force of F over a distance delta x, then the work W is defined to be the force times the distance. And that's it. Now, the reasons for that, I'm not going to go into them here. You go into a physics class, you'll see how this is related to the energy. Essentially, the work is the amount of energy that ends up getting put into the object, but that's kind of, like I said, I don't want to go into too many of these details here. Suffice it to say that this is an important quantity in physics. Now, what if I have a force on an object? Well, two things to notice. First of all, it's actually not just force times the change in position. It's actually the directional force. So if the force is in the same direction as the movement, then this becomes positive. If they are in opposite directions, then this is negative. So if the force on the object is fighting the direction of motion, then we call it negative work. If it is in the same as the direction of motion, then it is contributing positive work. An interesting thing about this, by the way, is that generally speaking, if you take an object and you move it around and it comes back to where it stopped, like where it stopped, if it stops where it starts, then net total, you have done zero work to the object. So when you go and you lift weights in the gym or something, you have ultimately, in the physics sense, done zero work. Although that can differ depending upon, that is true with what are called conservative forces. There are exceptions to this rule that I won't get into here. Anyway, what if the force is not a constant? What if the force actually depends upon the position? So, what if the force is actually a force as a function of x? Well, in that case, what we can do as we move from A to B, what we can do is we can approximate. At this point, you should be used to the fact that we're going to be approximating things because we do this basically every single day. We come up with an approximation. What we're going to do is, supposing that the force is continuous as a function of x, then over a small interval, the force is approximately a constant. So what I can do is that I can say, split this thing up into n pieces, and then from xi to xi plus 1, f of x is approximately equal to f of xi star, where xi star is some point chosen between xi and xi plus 1. Again, this is a very standard thing by this point. And so we can say that the total work is going to be approximately the sum from 1 up to n of f of xi star times b minus a over n, because b minus a over n here is really the change in x from xi to xi plus 1. But this is just a Riemann sum, so this is going to approach the integral from a up to b of f of x dx. And there we go. So let's think for a moment about some applications of this kind of thing. Here is one application of this, which is kind of straightforward. Well, sort of straightforward. Let's suppose that we have a spring. And let's suppose it has a rest position of x is equal to 0. And we compress it to x equals -2, and release it with a ball on it. And suppose that the force as a function of x is going to be -3 times x. And we want to know, or not what, how much work is done as it returns to x equals 0. Now, little caveat here of what's going on, because normally the spring would keep on going past x equals 0. The reason that I'm going to think of it this way, the reason why I might care about this sort of thing is maybe I'm using the spring to launch something. Like maybe I've got like a baseball launcher or something that I'm setting up to do this, and I'm going to make this launcher work by you compress the spring and then you flip a switch and it releases the spring. So maybe what we do is we stop the spring when it hits x equals 0 and we let the ball keep on going. So in that case, it would make sense to just ask how much work we do as it returns to x equals 0. The other thing I want to notice is that technically we should probably worry about the units here, like kilograms and newtons and joules and things like that. However, I'm just going to show you how to do this with the numbers and not worry too much about the units. Remember, units will always just come along acting like constants. That's the great thing about units. They're basically just constants. So whatever units you're working with, be they kilograms or pounds or whatever, they just treat them like constants. Okay, so well, what we're going to do is we're going to do the integral from -2 up to 0 of this force times dx, -3x dx. And what is that going to be? Well, that is going to be -3x squared over 2 evaluated from -2 up to 0. So plugging in 0, that gives me -3 times 0 squared over 2, and then I'm going to have minus -3 times -2 squared over 2. This, of course, just cancels to 0. This becomes +3 times +2, which comes out to be 6. And that's the amount of work that we have done. The reason why you might care about something like this, again, it's because in physics, the amount of work is related to the amount of energy that is put into the object. So if I want to know, okay, how much energy is this baseball going to have that I'm shooting out of this launcher with a spring, I can use this method to figure it out. This is also something that's important when we're talking about a lot of other things. Like, let's say that you're talking about somebody who is working for NASA on designing rockets. Well, one of the important questions is, does our rocket actually get this thing into orbit? Or does it crash and burn? You know, that would be bad. And it turns out that one of the ways you answer that question is you figure out, well, how much energy does it take to reach orbit? There are ways of doing that you would learn in physics, and then you can ask, okay, so how much work do we need to do to get the thing up there, and then how much does the rocket provide? And so it really becomes a very practical question. You can think of other situations too, like other kinds of projectile launching. Maybe you're not launching it with a spring, maybe you're launching it with some other kind of force on it, but it's that kind of stuff. You could even think about, like, let's say that you're studying archery and you want to study, like, maybe you're studying medieval history and you want to understand the history of, like, longbows and things like that. Well, how much energy is being put into an arrow? Yeah, all of that is going to depend upon the force that's being applied to the arrow over the distance and things like that. So lots of different questions that you can answer like this. As another question, and this one might seem a little bit tricky, but it turns out that it's actually even easier in some ways than the spring question, we could ask, how much work does gravity do to an object of 3 kilograms as it falls 10 meters? Well, this one's actually even easier. We almost don't need to go into an integral. And the reason is because the force of gravity is always going to be equal to 9.81 meters per second squared times the weight of the object, which is 3 kilograms. And so this is going to be approximately equal to, oh great, what is it going to be approximately equal to? 28.63, I think, because 27 and then no. 29.43. And one dropped pen. So 8 times 3, that would be 2.43, and then plus 27, that's 29.43 kilogram meters per second squared. That's going to be the force. It is a force in the downward direction as this thing is falling, and so the overall work that is going to be done is going to be 29.43 kilogram meters per second squared times 10 meters. So the overall work is going to be 294.3 kilogram square meters per second squared. Okay, now as you can see, I didn't need to bother with an integral for this one because the force was constant. So why did I go back to this simpler example? Well, the reason I wanted to go back to this simpler example is because it turns out that there are some kinds of questions that we can ask where this kind of thing is going to be necessary, and it's going to let us set up a different kind of integral in order to answer our questions. So let me explain the sort of thing that I'm looking at here. And a lot of these problems have to do with pumping liquid in and out of tanks. So